Okay. Last topic we want to talk about in this brief introduction is vector spaces. Now, I want to start out by talking a little bit about 3 dimensions and how we would represent vectors in 3 dimensions. It's really quite simple. We just add a 3rd component, as you'll see in a minute. Okay, so what do I have here? Well, I want that to be a picture of a box. Front of the box, top of the box, side of the box. Hopefully you see it that way. Now, I want to have a vector that goes from the lower right front corner to the upper left back corner. So there's a vector. Now I want to draw that vector on a coordinate system. So I draw an x, y, z coordinate system. I draw it like this, and you can see I can take that box and set it down here and make sense of the x, y, and z directions. What I'm actually going to do is go ahead and draw the box, and I'm going to set it here, so that the initial point of this vector, we get the origin. So I'm not probably going to get a perfect picture of the same box, but we'll have a plausible picture. Okay, so that represents this sort of a box. And of course our vector is here, and we don't want it to look like the vector's crossing the front of the box, so I'm not sure that makes any difference. I'm not sure what I did makes any difference. But right here is a vector that goes from the origin to the back left upper corner, back upper left corner, whatever, of the box. Now if this box has dimensions, let's say the dimensions are 3 in this direction, 1 in this direction, 2 in this direction, then we could say that the x component of this corner is -2. Okay, because this, I'm sorry, -1. This side would be 1. I haven't drawn it quite right, but we won't worry about that. This side could be 1. So if this side is 1 and we're going in the negative x direction, because the positive x direction is here, then the coordinate here is -1. That would be our x coordinate. Our y coordinate, well, along the y-axis, we have this side, which corresponds to the 3. It's also in the negative direction, so that would be -3. And then a z component, well, how far do we go in the z direction? We go 2 units in the z direction. So this point is -1, 3, 2. The vector from the origin 0, 0, 0 to the point -1, -3, 2 is what? Well, we haven't done any vectors in 3 dimensions, but it's not hard to see what that would be. The x component is going to be -1, the y component -3, and the z component is going to be 2. So, that's a typical vector in 3 dimensions. We have to have 3 components, 1 for x, 1 for y, 1 for z, and that tells us the displacement corresponding to the vector, okay? And we treat these vectors exactly the same as we do vectors in 2 dimensions. If I have 2 of these, I can add them. If I multiply one by a number, I get a vector that's that many times longer. If the number's negative, it's in the opposite direction. All those properties, okay? I can multiply this vector by a matrix. Now, the one thing that you have to have, of course, is this column has length 3. In other words, it has 3 numbers. So each row of a matrix would have to have 3 numbers. Would have to have length 3. but there's nothing all that new about this. If I wanted to have vectors in 4, 5, or 6 dimensions, I could do it. I wouldn't be able to draw them. I can only draw 3 dimensions. We only live in 3-dimensional space. We have no idea what a 4-dimensional space would look like. Okay? So, anyhow, there's a vector in 3-dimensional space. The length of the vector, we're not going to prove it right now, but very, very simple to prove. You just take the square root of the sum of the squares of the components. And I'll actually draw you a little picture. Right here is a vector whose length is square root of 3 squared plus 2 squared, right? Now, this vector and this vector are at right angles, so that we take the square of the length of this vector and the square of the length of this side, and we're going to get the square of the length of our yellow vector. So that's the only picture you need. You got to be able to write down the symbols, and something we'll work on a little bit. So that's a vector. Everything we do with vectors in 2 dimensions, we can do with vectors in 3 dimensions. And there are things we can do with vectors in 3 dimensions that we can't do in any other dimension, it turns out, which is kind of interesting. Okay, the idea of a vector in 3-dimensional space.